In this video, we're going to talk about graphing polynomials. And one of the first things you have to know how to do is to discuss what we call end behavior of a graph. So what does that mean? Well, let's look at a graph that we're all familiar with. This is the graph y equals x squared. Okay, recall that y equals x squared is a parabola. Now, if you look at the end behavior of this graph, what they mean is what is happening at the extreme values of x. As x is increasing towards infinity, what is happening with the y value of this graph? And conversely, as x is decreasing towards negative infinity, again, what is happening with the y value? So for this particular example, as we move in the negative x direction, as x approaches negative infinity, we see that y is increasing. So this graph is said to have a behavior that is up on the left. And we designate that like so. The same graph, as we move to the right, as x approaches infinity, positive infinity, y is also increasing. So we say that this graph is considered up and up. Up as x approaches negative infinity, up as x approaches positive infinity. And I want you to take note that x squared has an even exponent. As we'll talk about, when polynomials have an even exponent, the end behavior is the same. Now, it could be down, down, or it could be up, up, but they are going to be the same. Okay, let's now talk about another equation that we're also very familiar with. This is the equation y equals x. Now recall, y equals x comes through the origin at a 45-degree angle like so, has a slope of 1. Now don't forget, y equals x has a hidden 1 as an exponent, and that 1 is an odd number. Now notice what's happening with y equals x to the first power. As we move, as x approaches negative infinity, the y value is decreasing. So we say that on the left, the graph is considered down. On the right, as x approaches positive infinity, y increases. So we say that that is up. So we have a graph with an odd exponent that is down, up. The end behaviors are going to be the opposite. It turns out, ladies and gentlemen, that these two graphs, y equals x to the first and y equals x squared, are going to be the key to determining end behavior, in my opinion, of these polynomial graphs. Now, there are plenty of charts out there where they'll have x to the first, down, 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 up, x squared, up, up, or down, down, x cubed, down, up, down, etc. Now, you can memorize all these charts if you want, but if you just refer to these two examples, memorize those, and memorize the fact that x squared is going to behave like all the even polynomials, or I should say, all even polynomials are going to behave like x squared, and all odd polynomial degrees are going to behave like x to the first, then you don't have to memorize any charts. Okay, let's now look at some examples. let's look at f of x equals 2x squared minus 4x minus 3. And we want to discuss the end behavior of this polynomial. Well, the first thing we do is we look for the degree of the polynomial. That's going to be the highest exponent value, and that's going to be 2. So we know that this graph is going to behave like y equals x squared. Now notice something. The leading coefficient is 2, specifically positive 2. Therefore, this polynomial is going to behave like y equals positive x squared. And as we talked about in the opening of the video, that's what y equals positive x squared looks like. It's going to be up, up. So the fancy way to say that is as x approaches negative infinity, y approaches positive infinity. And then as x approaches positive infinity, y also approaches positive infinity. But again, you'll see that written either in fancy math lexicon, like is shown here, or you'll just see it as 2 up arrows, as in up on the left, up on the right. Now, ladies and gentlemen, I want you to imagine for a moment that the polynomial that I provided to you was not y equals positive 2x squared, but rather y equals negative 2x squared. And let's talk about how that changes things. Okay, so I'm going to put a negative in here. Now, this graph is going to look like, in terms of its end behavior, y equals negative x squared. And if you remember, y equals negative x squared is just the parabola reflected over the x-axis. Y equals negative x squared has a down, down profile, meaning as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches negative infinity. So that minus sign means you analyze the opposite of the baseline graph. Okay, let's look at another one. Let's look at y equals x to the 5th plus 3x cubed plus 1. And let's just consider its end behavior. This is a 5th degree polynomial because 5 is the largest exponent. 5 is odd. Therefore, this polynomial is going to simulate, in terms of its end behavior, one of our favorite graphs, y equals x to the 1st. Odd, odd, plus, plus in front. What's the end behavior of y equals x to the 1st? Well, as you move to the left, y is going to be going down, and as you move to the right, y is going to go up. Again, if it's odd, these are going to be opposite. So the end behavior of this fancy polynomial is just the same as good old y equals x minus 1. Now we're going to do the same here that we did in the previous example. I'm now going to change the sign of the polynomial to negative. And let's see where that takes us. Okay, what I'm going to do is I'm going to stick a little negative here. That means that instead of behaving like y equals x to the 1st power, it's going to behave like y equals negative x. All right, recall, y equals negative x looks like this. It has a negative slope. We learned back in algebra that that is a negative slope. What else do you notice? On the left, it's up, and on the right it's down, meaning as x approaches negative infinity, this graph, y equals x, which, by the way, again, to remind you, is y equals x to the first, is going to be up, down. So that is how this graph is going to behave. Up on the left, down on the right. Okay, now that you understand end behavior, which is very crucial to graphing polynomials, let's move towards looking at the polynomial in more detail. So let's look at this first one. Okay. The intuition on this graph is that because it's a third degree polynomial, it's going to behave like y equals x to the first power. There is no negative out front, so therefore it's going to look in terms of its end behavior like y equals x, which means its end behavior on the left is going to be down and on the right is going to be up. Okay, so that's the first thing you want to find, is what is the end behavior. Okay, what else do we need to know to graph this polynomial? Well, the first thing you need to do is ask yourself what degree it is. So it's a degree equals 3. That means at most there will be n minus 1 or 3 minus 1 or 2 turns or turning points. All right, so that's what you know about the degree. You take the degree, you minus 1, and that tells you how many turning points you can have. So that means the graph can't look like this. Okay, it's too many turning points. Third degree could have at most 2. Now, it could have less than 2, but it cannot have any more than 2. Okay. What else can we tell? We need to find the so-called zeros. Now, what is a zero? A zero is where a graph crosses the x-axis. So these would be the zeros of this particular graph in yellow. That has nothing to do with this one in white. Zeros are also called solutions, and they are also called roots. And the reason is, these are the points where y equals 0. Anytime a graph crosses the x-axis, y equals 0 in each of these points. Look, here it is. Here's the y-axis. What's our y value here? It's 0. It's neither positive nor negative. Right there, our y value is 0. The x value is changing, but the y is 0. And why is this important? Because that's how we see these polynomial equations. You're going to have x cubed plus 3x squared plus 1 equal to 0. And when x equals these points, these are solutions to this equation. These points are going to make this equation 0. That's why they're called solutions. That's why they're called zeros. I'm not really sure why they're called roots. Now, how do we find zeros? They're crucial to us being able to graph these polynomial expressions. Well, what you try to do, ladies and gentlemen, is factor this. Okay, now what does the word factor mean? Factor means you take an equation like this, which has two terms, right? X cubed and negative 2x squared. They're terms because they're separated by a plus or a minus sign. This is a term. And what we do is we try to create factors. Factors are two entities that are multiplied by each other. A term has a plus or a minus between it. So how do we do that? Most of the time it involves taking out the greatest common factor. So if I want to factor this expression above, I want to pull out an x squared, and then I'm going to be left with x minus 2. Now you always want to double check your work and redistribute. X squared times x to the first is indeed x cubed. Remember, when we're multiplying and the bases are the same, we are allowed to add the exponents. And then x squared times minus 2 is indeed negative 2x squared. And then what you do, so this has been factored. These are two factors now. Then what you do, folks, is you take each factor and you set it equal to 0. You want to know where y is going to be 0. So you place 0 for y and then ask yourself, what is going to make this equation 0? Well, if x squared equals 0, 0 times whatever's in here is going to be 0. And when this equals 0, so that's what you do. You take each factor and set it equal to 0. And then you solve for x. So here, our 0, or our solution to this equation, or our root, is going to be x equals 2. And on this side, it's going to be x equals 0. All right, so let me do some erasing over here. Okay, we already know what the end behavior is. Let's move this up here. Sorry, my dog is getting a little restless. Sorry for this delay. Okay, so now we have our zeros. Now what do we do with those? I think we are now ready to graph. So let's do that. We know that our graph is going to cross the x-axis at x equals 0 and x equals positive 2. I forgot to solve for x here. Now, what's going to happen in the interim? So what do we know? We know that on the left, this behavior is going to be down. So we know the graph is going to start like this. And we know on the right, the graph is going to be up. So we know when the graph finishes, it's going to look like that. All right, so let me put arrows on each of those. That's what our end behavior helps us. Now, you see this here, the fact that this is a 2 on this 0. You can also write this as x minus 0 squared. The fact that that's even means that for this 0, the graph is going to bounce off that point. It's not going to go through. When the root is 1 over here, because that's odd, the graph is going to go through the x-axis. So this is what's going to happen. The graph is going to approach x equals 0. It's going to bounce. Then it's going to do something down here, and it's going to go through like that. And that's going to be your graph. If you want more information as to what's happening over here, okay, remember this is going to be x equals positive 2, and this is going to be x equals 0. If you want to know some more details as to what's happening, you can plug in 1 for this and see what you get. So in this case, if you plugged in x equals 1 here, you would get 1 minus 2, or negative 1. So the graph probably doesn't go down as far as I've shown. It's more like this. So let's review what we did. First thing we did was we determined the end behavior. We looked at the fact that that was odd. There was no negative sign. Therefore, it's going to behave just like y equals x to the first power, which means down on the left, up on the right. The next thing is we factored it, and we set each factor equal to 0, and we solve for x. Those are the points where this graph is going to either touch or go through the x-axis. It touches and bounces off when the exponent of this root is even, and when the exponent of this root is odd, it goes through like it did here. The other thing we can do on these graphs that help us get a sense for the shape is get the y-intercept. To do that, we set x equal to 0 because, again, this is where x equals 0. That's going to be the y-intercept. If we plug in 0, we get y equals 0. So the y-intercept, it turns out, is also a root or a solution or a 0 in this particular equation. Okay, let's look at another one. Here we have this equation. This is a polynomial. All the exponents are non-negative integers. What is the degree of this equation? The answer is 2. 2 is even, and this is a plus sign. Therefore, this equation is going to look like its cousin, which is y equals x squared. It's going to be up and up. Now let's try to find the zeros. We're going to factor this, and when we do, we get x minus 4 to the first power times x plus 2 to the first power. We're going to set each of these equal to 0. X minus 4 equals 0, x equals 4, x plus 2 equals 0, x equals minus 2. We're ready to plot. Okay, let's do that. Let's move that out of the way. And let's plot the zeros. So when x equals plus 4 and when x equals minus 2, we know that this graph is going to touch the x-axis. Also, the fact that these are odd means at each of these zeros, it's going to go through the x-axis. We have an up-up situation, which means the graph is going to be up over here, and it's going to be up over here. As we approach this 0, we know it has to go through. We also know that it has to end up and go through this 0. So we know there's going to be a turning point here. Now, one of the things we can do right here, ladies and gentlemen, is we could find this y-intercept. That'll give us some intuition in terms of how low this goes. Does it come here or does it go lower? We're going to know based on the y-intercept. How do we find the y-intercept? We plug in for x equals 0 because this is the y-axis. This is the y-axis. And what's the value of x on the y-axis? It's 0. So we plug in 0. Now, when you plug in 0, don't do it here in the factored form, because then you have to do this multiplication and you might make a mistake. Put the 0 up here. So that gets rid of this term, since 2 times 0 is 0 and 0 squared is 0. And it just gives you the only term that doesn't have x. So it's going to be minus 8. So there's your graph. Up and up. Y-intercept of negative 8. It has a degree 2, which means at most one turning point. And it goes through negative 2 and positive 4. And when it goes through, it goes entirely through. There's no bounce here. That's because each of these roots, each of these solutions, each of these factors have an odd exponent. Next one. Okay. Now, in this particular case, we have a third degree polynomial. That's odd. There's no negative out front. Therefore, this graph is going to behave exactly like our good friend y equals x to the first power. And how does that graph behave? It's down, up. As x approaches negative infinity, it's down. As x gets larger, positive infinity, y goes up. It's a third degree polynomial, so at most 2 turning points. Now let's factor it and find the zeros. Pull out a GCF. In this case, it's going to be x. We can then factor that. Okay. Set each equal to 0. We get x equals 0 and x equals -2. What do we notice about these two zeros? This one has an even exponent. This has an odd exponent. Therefore, when we do our graph, we label our zeros. We know that at this 0, the graph is going to bounce. It's either going to bounce this way or this way. Here, it's going to go through. Okay, now let's plot our graph. Where do we start? We start down, because out here, this graph is going down. So we start down and we approach our 0. We know this is going to be a bounce situation. Now again, where does this graph cross the y-axis? What's our y-intercept? Excuse me. The y-intercept is going to be 0. So if we plug in x for this, we're going to get y equals 0. So we know this graph is going to cross there. That's the y-intercept. It's not going to cross the y-axis down here. So that gives us some intuition on the behavior of this graph. There's going to be a turning point somewhere between -2 and 0, because it has to do this. Now, we also know, because 0 is one of our solutions and it has an odd exponent, that it's going to go through the graph, through that 0. So that's what we're going to have. And again, if you wanted some more intuition as to how low this is, you plug in -1 into here and you see what y evaluates to. I mean, I don't know. It could be way down here and then come up. But we don't really need to know that for this particular video. Next one. This one is already in factored form. That'll save us a few minutes. Okay. So what do we know about this graph? What is the degree of this equation? Well, if you have a 1 here, you add up these exponents. This is a third degree polynomial. That means it's odd. We look at the leading coefficient. There's a positive sign out here. That means this graph is going to behave just like y equals x to the first power. Odd, odd, 2 plus 1 is 3. There's no negative sign out here, therefore it's going to behave just like this. It's going to be down on the left and up on the right. What are our zeros? Well, we set that equal to 0 and we get x equals -5. We set that equal to 0 and we get x equals -2. Okay, we are ready to plot. At x equals -5, there's going to be a 0, and x equals -2, there's going to be a 0. because this is even, this is going to be a bounce situation at -2. Okay, -5, it has a 1 as an exponent. It's going to be a through situation. The other thing we can do, folks, is find our y-intercept. Let's do that. X equals 0, we're going to have 3. If we put 0 here, we're going to have 5. If we put 0 here, we're going to have 2 squared. And that's going to end up being positive 60. Okay, so we know our y-intercept is going to be way over here, or way up here, I should say. Okay, so the down up tells us we're going to start down. The fact that as we approach this 0, it's -5. That has a 1. That's odd. That means we're going to go through the x-axis. So let's do that. Okay. We also know that this is a 0. So we know at some point in this interval, this graph is going to have to come back down. Now, we don't know how high it goes before it does that. To figure that out, we would plug something here in the middle. We would put in x equals -3 and see what y evaluated to. But we're not going to do that. We're going to turn this graph back down towards -2, where we know it's going to touch or cross the x-axis. Because at this 0, we have an even exponent, this graph is not going to go through. It's going to bounce off that, and then it's going to head to the y-intercept. Bounce, and then go to the y-intercept. That's your graph right there. Notice it's a third degree. It can have at most 2 turning points. 1, 2. It's down and up because it's a third degree polynomial. It simulates good old y equals x to the first power. And there's no negative out here that switches things around. Okay. This one is going to involve some factoring. We know third degree polynomial. No positives, no negative sign out here. This is going to behave like y equals x to the first power. It's going to be down on the left, up on the right. What else do we know? Our y-intercept. Let's do that right now. Plug in 0 for x. Here's our y-intercept. So -45 is our y-intercept. To find out any other information, we have to find the zeros. We have to find the points where it crosses the x-axis. So how do we do that? What we do here, folks, is factor by grouping. So we're going to look at this part of the equation, and we're going to pull out an x squared. And over here, we're going to look for another x plus 5. So once we pulled out this x squared and it revealed this x plus 5, we knew that there had to be an x plus 5 here. So when you distribute this -9, you're going to get -9x minus 45. Now what we do is we say to ourselves, well, this x plus 5 is indeed a GCF. And then we notice that that's the difference between two perfect squares. So when all the smoke clears, we get x plus 5 times x plus 3 times x minus 3 equals y, and we're going to set that equal to 0. Okay, let me make some room. This is what we're going to work with. It's a third degree polynomial. we ask ourselves, what's the exponent on each of these roots? Some books call that the multiplicity. These are all odd. Therefore, they're all going to go through the x-axis. There's going to be no bouncing in this particular graph. Now, don't forget, we have the benefit of the y-intercepts. We know it's going to cross there at -45. We know that this 0 is going to be -5. This is going to be -3. And that's going to be +3. Recall, we get that by setting each factor to 0 and then solving for x. Okay, so let's plot those on our graph. So we have -5, we have -3, and we have +3. We know that our graph is going to start down. We know because as it approaches this root, because that is odd, we know we're going to go through. We know we got to get down here because that's our y-intercept. So we know there has to be a turn here. As we approach -3, again, we check the exponent. We got to go through. So we're going to come down here. Now, we don't know if this is a turning point, or we don't know if the graph comes here and turns down here. How would we answer that? We would plug in x equals +1 and see what y evaluates to. All right? When you do that, I did that, and you get y equals -49. Okay, so what happens is, in this particular graph, is it doesn't turn up at the y-intercept. Okay. It goes all the way down, at least this far, to -49. And we don't know if it keeps going before it turns, but this is good enough. So now it's going to come up here through +3. We know that the behavior is down, up. We've satisfied that. We know when we go through this 0, we go through it. We don't bounce off it because that is an odd number. So that's our graph right there. Okay, I believe we had one more. We have y equals x cubed plus 2x squared minus 4x minus 8. What's the intuition on this graph? It's a degree 3. That's odd. That means it's going to look just like y equals x to the first power. It's going to be down on the left, up on the right. What's the y-intercept going to be? -8. Okay, let's put that over here. All right, all we did was plug in x equals 0 to get the y-intercept. We know it's end behavior. We know the y-intercept. If we want more information, we have to find the zeros. To find the zeros, we have to factor. Okay, let's pull out the GCF on this part of the equation. We're going to have x squared is x plus 2. Now we know there has to be an x plus 2 here. So we ask ourselves, what goes here? Alexa, cancel. We ask ourselves, what goes here? I'll put a question mark. To create this. It's none other than -4. -4 times this will give us -4x. And -4 times the +2 will give us -8. All of these problems work this way. Once you get this factor, you look for it over here. In fact, you insert it there. and then you figure out what that question mark is. So I'm going to put a -4 in there. Now we're going to pull this x plus 2 out as the GCF. And we're going to have x squared minus 4. And this is the difference between two perfect squares. So we're going to end up with x plus 2 times x plus 2 times x minus 2. And this is going to simplify to x plus 2 squared. Okay, let's make some room. Let's plot our axis. Now let's put our zeros and let's analyze them. This 0 is going to be x equals -2, and we're going to bounce off it because that's even. This is going to be x equals +2, and because that's odd, we're going to move through it. Okay, let me plot those. So here's -2, here's +2. Let's not forget our y-intercept. It's down here. It's going to help us. And let's go to work here. Okay, this is going to be a bounce. Okay, I'm going to bounce here. So we're going to start down over here. We're going to bounce off this. We're going to head down through this y-intercept. And at some point, we're going to curve back. And when we hit this 0, we're going to go straight on through because that 0 has a 1, namely an odd exponent. So let's do that. Start low. We bounce. We come down here. We come through the y-intercept. Now, we don't know how far we go before we turn around. But we know we have to turn around and go through. There's your graph.